Swayam Prabha. Digital India. Educated India.
Of course, without the other points like not only observation but also understanding, the entire thing is a waste, right? All right. Of course, pull it fast and see if it breaks. It breaks very nicely. Why does it break? Now I have an explanation. Now I have an explanation. Why was it plastically deforming? So higher force will have smaller duration. Yeah, correct. Good observation. Impulse, yes. Observation. Correct. Fantastic, Ashwin. We give time for it to slide across. Else, oh my God, I'm finding it difficult. Separate. And if you do it, you get a very nice surface. You have a look at the surface. Right? It just splits across, over. Got it? By the way, you played with this when you were young. This is called silly putty. It's very silly, no? So, silly putty. All right. I'm going to show you one more material. Interested? Gooey material. It's like jelly material, right? I'm going to ask you a question. What shape is this? Disc shape. Gooey material. I stretch it. If you stretch the gel, what will happen? It will easily stretch. And I leave it. It comes back. Look at this. If I throw it onto the board, what should happen? Like a fluid, it will just splash. I don't know if I can do that, sorry. And then it comes back. The clay that you have, no? The clay that you have, where is my clay? Yeah, here. The clay that you have, let's examine whether this clay is a special clay, okay? Okay, so I'm going to do something. At the end of the lecture or session, we'll find out what really happens, okay? Okay. Okay. Can someone guess what would happen to this? It will fall down. It will elongate. Yeah? It will elongate. Let's see if she is right. What's your name? So we'll shrink her name again, Day. So what I will do is, I'll take this, put a weight below, Hey, nothing happens here. Oh no, nothing happens here. Nothing. Try it out. No, you have it with you. Try it out. What happened to your there? You want it? He's pulling it. Elongate. It's becoming longer, no? Longer, longer, like the hair, longer. I decided to grow long hair like my son. Wanted to compete with him. Yeah. So this property, which is not existent in this one, after a very long time also, I'll see that this will be a disk. Unlike that, when I do the same thing on this, I made a small disk-like stuff there. After some time, what should I expect now on that? What should I expect? Who can answer this question? This is a little tough question. I have stuck this silly putty over there. After some time, let's say 1 hour, what do I expect to happen? Any guesses? It will stay. No, you know the mass. It will slide down, or we'll use one word for it. Supposing I take this and put it in this box, as a sphere. After about, let's say 2 hours, what do you think I would see? It will take the shape of the box, yeah? Tell me one material that takes the shape of the container. So what do you think will happen there? It will it will flow. My mentor used to tell me that every material is capable of flowing. It is just that in the short period, I look at it as elastic, etc., etc. But every material is a material that flows. Okay. Short term is long or long term is the question. All right. And that brings us to the other point. Even the structure, perhaps about 2000 years from now, would have sort of caved in. Okay. Because every material goes through this kind of a thing. This is called the viscoelastic property. Okay. I will not go into details because it takes more time, but it's called viscoelastic property. Okay. Just wanted to give you ideas of two things: plastic deformation is occurring or it is separating. When it is plastic deformation that is occurring, we'll call those materials as ductile materials. When it is like piece of chalk, we'll call those as brittle materials. Now, watch me carefully. I take this material. Shall I bend it? Oops, it's breaking. So this is brittle. No, I'm saying this is ductile. Counter me. I'm saying this is ductile. Wonderful. Well, she deserves 2 chocolates. What's your name? Manasa. I can't hear. Can you hear her name? Manasa. Yeah, explain.
I said that it's ductile when it's
I'm
heated.
Manasa.
Okay, I'm Manasa. I said that when it's ductile when it's heated, but at room temperature it's brittle.
Wonderful answer. Here. So, I cannot state this is brittle or ductile unless I know under what conditions. Actually, let's see. Do I have a... there you go. Let's heat it now. Come, Manasa. No, I'll heat it. You use pair of scissors. Cut it. Yeah. Can I cut a piece of chalk using pair of scissors? Huh? You can. Let's see. This is brittle material, no? Supposing I use a pair of scissors. Hey, why are you using pair of scissors is what you're going to ask me, correct? That means you don't feel good using a pair of scissors with this material. Why? Yes, it is brittle. It breaks, correct. It breaks. It's not a nice cut. It is not a nice cut. Oh my God, this is just chipping apart, correct? It is happening because, Ashwin, you can answer? Because you've been answering this plastic deformation questions. What is the pair of scissors doing? Applying? Sliding force. What is that called? Shear. It actually should not be called a pair of scissors. It should be called as a shearing instrument. Okay? As engineers and scientists, we should not call this as a pair of scissors. For somebody else who is not that, it's fine. This is a shearing instrument. If I use the shearing instrument and cut, I am doing a mistake because the material is not going to fail by shearing. Okay? What should I do for that? In order to fail nicely, I'll use a knife and do that, because now I'm creating a stress to split. All right? But Manasa is going to demonstrate. This side is fine. Come. You will cut it. Okay? So she is going to use a pair of scissors. Where is we need to spot a place where, how about here? This is fine? Not much over here, right? So I'm going to just heat it a little bit. This end, yeah, I've done it. Yeah? Okay, you cut a small piece here. Wow, look at that. Fully. Yeah. Nicely cut, no? The reason why it is nicely cut is because when it becomes ductile, it is able to now help in terms of sliding across between the two. It is also one more thing. So I want you to get up. Yeah, slowly getting up. All right. Now.
So, does it form a like lattice structure? Does it form an organized?
Yeah,
lattice?
yeah. No, I'll tell you. It is not lattice structure as such. I'll explain to you. That's why I asked you to stand up now.
When we heat it, is it because we are allowing the layers to slide?
That's what we are going to now experience. See, remember, I'm going to help you with experiencing it. Now, you're now standing, let's say, let's assume that you're all holding hands with each other, okay? That's the bond. Suddenly, I'm asking you to go and dance, okay? What will happen to you? You don't have enough time, space, so you ask the other molecule to move, right? You get more space, correct? Yes or no? Right? Yeah, the molecules get kinetic energy. The kinetic energy is your dance. When you dance, what happens is you need more space. When you have more space, then the bonding also is affected. When the bonding is affected, when you use a pair of scissors, you have enough space for you to cut through. Thank you. You can sit down. So it's the kinetic energy that I have supplied. And it all depends on what material it is. Okay? If I take a piece of rubber, it is already in that state. So it's okay. So what temperature matters in terms of what matter I'm using. Is this clear to you? To a certain extent, is it clear? Every material that is plastically deforming plastically deforming, I can use a pair of scissors because it's a shearing instrument, right? And I can nicely cut. How about a piece of paper? Yeah? How about a sheet of metal? If I heat it? Thin sheet. You can see it. It cuts, no? Nicely cuts. No problem at all. Plastic sheet? Do I have a plastic sheet? Yeah, plastic sheet. Why is it possible for me to use a shearing instrument in order to cut the metallic sheet? Right, I can just slide it through the layer. How about this one? This is made of what kind of molecules? Polymers or chain-like molecules. So shall I use a pair of scissors, shearing instrument? Yeah, I can use a pair of shearing. Of course, if you go closely and look at it, it is not actually perfectly a single surface here. Okay, so there will be, but it can find more and more of those weak bond situations where it can separate. All right. Okay. So we have understood quite a few now in terms of brittle, ductile. The material need not be ductile or brittle, but it depends on temperature is only one field. It is external conditions, or we call this as state of the material. We did this CD cover, we did a piece of chalk, we did. We felt that these are brittle and ductile. Okay, we'll come to that. Before that, we also found that if we heat it, the state of the material changes. State of the material depends on various factors related to that material. The temperature of the material, the what else? Temperature of the material. Huh? Yeah, temperature is one of them. Any other dimensions? Not material, no. Material may not have dimensions. Any other parameter that governs bonding? Temperature is a particular external condition, correct? So temperature is an external condition. What else? Pressure, force, very good. So the state of material is determined by the stress that it experiences. Madam, should there be a break between the first and the second lectures, or? No? Okay. Because if it is too long, you'll get bored, that's why. The second one is, so temperature, force or stress or pressure, okay. Any other? Point of application is again, you're talking about a spatial quantity. Any other? Wear and tear, no. We'll come to that. External conditions, no. Temperature. One more. You are in an air conditioned environment. You go outside, Chennai, humidity, right? So many factors govern how the material behaves. Okay, under various situations, combinations of these situations, it will be very different. Yeah.
Sheet, for example.
Come again. I didn't get the first one.
So in your acrylic sheet, if you use this pair of scissors, you get like a periodic
No, actually, a brittle material you cannot get. In fact, I have written a paper also on this is a brittle material actually, right? This is a composite material. To cut this is not easy with whatever saw that you use. There is a particular way by which you can cut this, because this material as such is brittle. You need to take it to a state where it becomes possible for you to nicely cut. So, a brittle material is tough to cut nicely if you use a pair of scissors, or in other words a shearing instrument. Any instrument that is not shearing but separating is perfectly all right. So, there are two instruments, which is a knife or a shearing instrument. The two act as, one is separating, the other is sliding. Okay. Okay. Volunteers. Yeah, one of you can come. Anyone? Adi has already done. Shraddha. Okay, come, Shraddha. Okay. One more volunteer from the girls. Because if I push her, she will fall down. Demo is about pushing. Whoever doesn't like Shraddha, well. Yeah, Ananya, come. One of you. Okay, you come. Manasa, you come. All right. Oh, she doesn't like. Oh, okay, then it matters now. Anybody else here wants to volunteer? No, okay. Come. So I'm going to tell Shraddha a secret. She overheard me. Okay, come here. Manasa is going to push Shraddha. Shraddha, keep yourself, make sure that you don't fall, okay? Just watch. Manasa is going to do the pushing first. Oh, you too much here. She's your friend. Okay, the second time you push. Okay, did you notice? Okay, again, the first time. Okay, you're coming this side, go a little bit that side. I also don't want to fall. Yeah, the second time. Oh. What did you notice between the first and the second?
The first time she was freely moving, but the second time
she was
also
freely
resisted
moving.
it. She also gave it backward.
She resisted. Very good. Okay. She's not noticing changes that way. Okay.
Second time she adapt.
Huh? After adapting. Okay.
Knew the force the second time better.
She knew the force second time.
The direction at which you apply the force has some effect on it.
Okay. You want to apply this? Apply in the same direction. Is that okay? She's going to apply in the same direction. Not turn this way, that way. Okay. The first time. Hey, Mansa, too much here. I know you don't like her, but yeah. Second time. Okay. Huh? This time, no geometry change. Yeah. Huh? Stance. What did you observe? Oh, yeah. The first time and the second time. What was the difference? The first time she was
Before approaching itself, she got she has to give.
Shrey, right? Shrey said first time she was freely moving, the second time she was resisting. Give me another word, set of words for that. Go ahead. This section of people are not responding. Oh, you came this side, okay. Except him. Yeah. First time was unpredictable. But first time and second time kept happening. So she could predict. Shraddha could predict. What did Shraddha do the first time compared to the second time? Huh? She gave more resistance in the second one. So give me a word that connects to these two. The first time what was? She was very flexible, very good. Manas, I suppose not answer, but anyway. The first time it was? Shraddha was flexible. The second time she was?
A lot more rigid.
Give me some other word for that. Stiff, thank you. Manasa and Shraddha, thank you. So a material also can behave that way, correct? Yes or no? A material can be flexible, can be stiff. What am I talking about? Whenever you have that kind of a face, I am going to use a bit. What am I talking about? From an aspect that we understood. No, that's too much. Observation. When she was flexible and when she was stiff, what did you observe? Manasa was pushing her the same. She wanted just out of her life. Huh? Opposing force. Yeah, I mean, push is there, no problem. But what is it that, yeah.
The property of the material man.
What observation did you have? Huh? What is that response? Very good.
The
Extent
extent to which it will differ.
to which it will deform. That's it, yeah. If a material does not deform too much, it is flexible. For the same force, if the material does not deform too much, it is flexible. Why are you not opposing me? It should be stiff. So if the material deforms a lot, it is a stiffer material. Flexible material. So you know now, if the property has to be examined, if I have to experiment, I want to use this as against the steel bar, I apply the same force, I apply the same force and ask that question. What is that question? Whether deformation is more or less. If it is more, it is flexible. If it is less, it is. And therefore, now when I come to another word which is deformation, there is a force and a deformation, or stress and deformation. Somebody used that word called strain. Strain. I'm just going to explain to you and then move on. A lot of things have to be done. So I hold it here, I apply the same force. I hold it here and I apply the same force. Same material. You're able to understand, no? In one situation it is stiffer than the other situation. Correct? So I should do some correction here. I should do some correction. I'll repeat it once more. Just listen to me carefully. Half the stick and I'm now pushing, it is deforming to a certain extent. But when I do the same thing for the full stick and apply the same force, it is deforming more, but the material is the same. I want to describe the material. What shall I do? What shall I do? Yeah. Define point of application.
You take force per unit length.
Fantastic. Not force. Exactly. Okay, I'll give it to you. Too many chocolates. Don't eat all of them. So, when I take the deformation divided by the length, I have removed that geometric quantity called the length, and what I get, roughly, crudely is called the strain. Just like for instead of force, I said force per unit area, now it is elongation or deformation per unit length, and if I take these two, I can now describe the property of the material, right? If I draw the curve, response curve, if the slope of that response curve is high, it means the material is flexible. If the slope is high, the material is flexible. Stunned faces. Stress, some sigma, let us say, strain, I got one curve like this and the other curve like this. This is that of a flexible material, this is that of a thank you, thank you. So this is that of a stiff material and this is that of a flexible material. So I understand these two, right? This we define by the slope of this, and the slope of this is called the modulus. Okay, don't use young. I don't want to associate with some scientist. It's better to say elastic modulus or just the modulus. Okay, it gives me an idea of what kind of material I'm using, and now we can say, okay, if it is flexible, the modulus is going to be smaller. Correct? If the modulus is higher, it means it's a stiffer material. Yeah.
Sir, could we have a material where within the elastic range, it is initially very flexible and then suddenly becomes very stiff, or it's initially stiff and then becomes
So
flexible?
what I have drawn here is only at a particular point. So there are many curves that I can generate. No, I can generate like this, I can generate like this, right? I can generate like this also, right? All these are possibilities for a material, okay? And therefore, if I do this kind of a test, I'll get an idea of how the material behaves, okay? Crude ideas are initially, if you look at it, small deformation, I can linearize it. And I can call that as elastic modulus. In the olden days, it was difficult for them to deal with anything that is non-linear. So what they did was, they made sure they worked only within the small region. That's why when you go to old buildings, huge columns. Why? Because they wanted to reduce the stress so that it behaves elastically. I know how to predict. As a design engineer, I want to predict properly, and therefore huge columns. Today you go thin structures, you are not very sure whether to buy that house or not. That's what happens. Yeah. Let me proceed further. I'm very, very slow, but bending the aluminum rod and bending the bamboo, you will get an idea of which one is stiff, which one is less stiff. Which one is less stiff? Bamboo, right? So if I take these two as the two curves, I know this is pertaining to bamboo, this is pertaining to stiff or soft. Flexible is also fine, but time dependency we already saw. There are two properties that you should know. One is viscosity. You all know viscosity, that is attributed to a fluid, and there is the other property that is attributed to a solid, which is flexibility or stiffness, or you can call it as elasticity also, right? If I combine these two, we will get materials which are visco-elastic, visco-plastic, and so on. All right, is this clear? Are these materials solid or fluid? It depends on which one is dominating, whether the solid is dominating or the fluid is dominating. All right, we already saw this. Any other question you may have? So that we have got only one third of what we should be covering, but if you have questions, you can ask, even if it is beyond this. Yeah.
Sir, is it possible, let's say we want to have a material which has a specific stress versus strain curve, like for example that kind of semicircular curve which you drew. Is it possible for us to design a material based on any curve which is there, like which does not intersect itself or go back like that?
So Adi is asking, let us say I have tested a particular material and I got a curve based on the testing that I have done, and I got the curve. Now, can I use this curve to design?
We are not testing. We draw whatever some random curve, and then we want to make a material which behaves like that.
Yeah. Yeah. Good. That's a very good question he has asked. He is asking, supposing I have a curve, can I mimic that curve by a material behaving like this? Wonderful. So what Ashwin is suggesting is, can I take two materials, combine them in a particular way? Yeah. So the answer to your question, Adi, is in terms of being able to, we use this word tuning the material. All right. As designers or materials people, we want to tune the material in such a way that whatever there is the need, it is met. For example, as a civil engineer, I look at this and ask the question, can I now have the material that is responsible for taking that particular amount of stress, etc., etc.? The answer is yes. Oh, okay. Concrete is a mix of many materials. One is a stone, we call it as blue metal, okay. The other is sand. The third one is binding material, which is cement. Cement, sand. Supposing I mix these differently, will I get different properties? The answer is yes. Now I have some tool with me, right? If I have experimented with many different combinations, I now have an idea, okay, I can now tune it in such a way that the need that I have is met. Have I answered your question? This is only one of them, which is concrete. There are other materials. I showed you this material. This material consists of two components. One is a resin, typically epoxy. The other, if you notice carefully, I don't know if I have it here. The other is actually a fiber, glass fiber. What do you know about glass? Glass. The word glass, brittle, right? Resin, flexible. I mix the two. What question will you ask me? What question will be asked? How do I make it this way or that way, right? Which is stronger? What do you mean by stronger? Before it fails, it will withstand higher stress if it is stronger, right? Many people think that bamboo is not very strong. Actually, bamboo is very, very strong by weight. Now tell me, is the resin stronger or the glass fiber stronger? That's what you think, no? Glass fiber is about 10 times stronger than resin, roughly. I'm just giving a rough figure, right? So if I mix, I'll get better property as far as strength is concerned, right? So if I give you something like this, which is like a CD sheet, and this you can easily break. Somebody wants to try to break this? Come and try. But be careful, safety is important. You want to try it? Come. He wants to break it. Always destructive. Yeah, Yeah, man. Ooh. Try it. This one, you want to try this? That's very easy, sir. Hey, be careful. Yeah. Your hand should be, yeah. Ugh. Oh my gosh. Okay, so how about this? I like your enthusiasm in breaking it. Now I'm going to ask him to combine it and make it one single piece. No. Good. What did you notice, Keith? Don't worry about it. It's okay. What did you notice? Be careful with your hand, okay? What did you notice? What's your experience? Oh, my hand, it's not breaking. Remember, these two are almost the same resin materials. All that has been done is the fibers are included here. The fiber is this. This is the fiber. The moment I include that, I can make it very strong. Almost the same thickness as the other one. Yeah, thanks, Keith. So you can tune it appropriately to get a better material. Any other question? So now power is to us. We can tune appropriate to our requirement. You can ask enough questions. I don't know how much I can finish, but
So what is the structural difference between a shearing instrument and one that applies?
yeah, a shearing instrument applies a force that is shearing force. It tries to slide one surface over the other. So if I take a piece of, let's say, a material, a block of this material, think of this block as delta x, delta x and y tending to 0. Okay? If the force is along the surface of this, it is called the shearing force. If the force is normal to this, it is called the normal force. The shearing force, if applied, and if the material is such that it can easily slide, it will easily slide with that instrument. If it is something that has to be pulled to break, then I will apply normal force. So if I take a piece of chalk and I pull it, I can break it nicely. I do the same thing with this, you know what happened, correct? With silly putty, you know what happened, correct? Hey, look at that, dear. It's already flowing. Yeah. So here, actually, the surfaces are sliding between each other. In fact, the chain molecules are sliding because that's the easiest path it can take.
So you said delta x, delta y tending to 0.
Yeah.
Isn't that an unreasonable assumption to make?
Yeah, because this is an assumption where I assume the material is a continuum. What we do, it's a very good question, Ashwin. What we do in our, as mechanicians, instead of dealing with molecule after molecule or a crystal, a small crystal versus small crystal, we'll take this as a continuum, which means that just like a field, it is a field of materials. If I move from one x and y to x plus delta x and x plus delta y, I will again find a material. Delta x and delta y tending to 0. Okay, that is called a continuum. So when I make a continuum assumption and then ask this question, what kind of force is applied? Remember, force here is on that surface which is very small, right? Delta F is the force, delta X or delta Y is the surface. So 0 by 0, as limit tends to 0, you get a finite quantity which is called the stress. Got it? Right? So if I apply and if I use an instrument that applies force along the surface of the box as opposed to normal to it, I will get a different result, right? In fact, you may ask this question, supposing I twist which is actually shearing, what will happen? You try it out for yourself, you will not get a nice surface, it will be a helical surface because it is trying to find out which direction it is, and that normal force goes to 0, goes to a higher value. Yeah.
So with
Good questions.
the resin and glass fiber you took, right? You said you bound the glass fiber onto the resin. How exactly did you do the binding process?
Okay, so I need to make epoxy now it's a solid. I need to make epoxy a liquid. How do I make epoxy a liquid? Yeah, so I'll take it to a higher temperature, or I can use another material that temporarily makes it fluidy. Once I do that, I can get it to flow with the fiber on it, and the result is what you get here. All right. You cool it down, you get this. All right. This is thermoset. What is used here is a thermoset polymer, which means that at room temperature is actually a brittle material. There are also materials like this. Where is that black cut sheet here? Here. This one is a thermoplastic material, which is at room temperature. This is, supposing I dip it in nitrogen liquid and take it out, it will be brittle, okay, because the state of the material now changes. Any other question? Yeah. Ask whatever comes to your mind, it's okay. Don't blame me for not answering.
So can we like predict the path of the like how it will break and what is the path?
Yeah, it's possible to do that when you go into micro mechanical analysis. This is something that we do. Okay, so we take from the continuum, we take one of them and put a structure to it. Let's say it's a crystal. I'll have the crystal there, apply the appropriate load on it, and find out what could happen. Okay, so that's called the micro mechanical analysis, to examine what really happens in the mechanism of either failure or deformation or whatever. For example, I'll give you an example. We'll come to this. This is called the tensegrity structure. This is a structure. So think of this as one cell in your body. One cell in your body. Your tissue is made of this. I'm not joking. It's made of this. I want to examine one single cell. Now it is not a continuum. What do? I apply appropriately. If you look at it, our heart functions like this. Press it, you can see the other one moving. I am only pressing this, but these two are moving, right? It's actually, so if I keep a ball inside, no? If I press like this, the entire thing gets crushed, right? This kind of structure is called tensegrity structure. All our cells are made of a very similar structure, okay? Where is yours? Thanks to Aishwari, we made one unit of this. You can see this. Aishwari, you can press it and show. So, yeah, you can use the yeah. So when you press it, it compresses. You can see that. You can stand and see if you want to. Yeah, you can use this here. Yeah. Okay. What I have done here is I have assembled 3 of them. The cell has grown. The cell can grow all over, and that's what we are made of as far as tissue is concerned, right? If I take that and look at the tissue and apply load, find out what happens, I'm looking at a macroscopic picture. At a microscopic picture, this is what it is, and I can analyze how this behaves, so that from this it is possible for me to understand how this continuum behaves. Is this clear? Am I talking too much? Fine? All right. This is what we call a structure. When I showed you this, you did not recognize a structure unless you went through at a microscopic level, right? This is a structure. Keith likes. Now he has given up. Come and try this. Tell them how heavy it is. It's very heavy. Very light, so it's easy to break. Right? Very light here. See, it's very light. Very light. So you can break it, no? Yeah, it's just simple. See, it's so light. You want to try? Are you able to even deform to 1 micrometer? Huh? Yeah, it is. What did you notice? Yeah, we'll come to that. I know many of you have not seen it. That particular one that I'm passing on, whatever you do here doesn't matter. Nothing will happen.
Can I try?
Yeah, of course. You're not heavy enough for it. You're not heavy enough for it, by the way, because I know it. You can crush this one, but not this entire thing. This, I'll have you feel it. Yeah, what happened, ma? Whatever you want to do. Okay. This one, once you feel it, you will know very light. This is actually what is used in the satellite material. Okay. You have what is called phase sheet here, one phase sheet here. If I remove it, what you will see is something like this, the hexagonal pattern. It is this structure, more than anything else, it is this structure which makes it very stiff and very light, which means I can now think of an aerospace structure. Yeah. It is actually not very expensive, because if I am able to make this, all I have to do is one sheet here, one sheet there, that's it. How do you make this? Hey, all of you have made this. All of you have made this. What you do is apply glue, one line here, stagger it, one more line, pull it. You got what I mean? Yeah, you can make, and you cut it. But this side, you will get as many pieces that you want as of this. Once you do that, take one sheet, do that at home. One here, stick it nicely, and challenge your friend to even bend it. You will see exciting stuff. This is called sandwich materials. Okay. Why am I talking about this? I am talking about this because I wish to convey that structure matters. This particular structure is very useful for me as an animal having tissue that is flexible enough also has all the other functions. By the way, how many of you know bone is brittle? That's what we think, no? Bone is actually not brittle. It is not brittle, it is as well strong compared to its components. I take two components, mix them together, it is stronger than each of the components, it is stiffer than both of the components. That's what bone is. Bone is not actually a brittle material. Brittleness comes at a particular stage, okay? This kind of structure matters a lot. The other structure is what I have shown you over here. There are many such structures that are possible. I have two more presentations. What should we do? We will continue in the next class. Yeah? That's tomorrow. Yeah? Tomorrow is supposed to be inventor's mind, but I will combine it and give you an idea of how you can be an inventor. How many of you want to be an inventor? Every scientist is an inventor because they discover or invent, correct? Yeah, every one of you can invent. I'll just give you three different tips. If you follow that practice, you will be an inventor. Nobody can stop you after that. Okay? Yeah? Except Adi. No, kidding.
Sir, with this material, you're sticking to place it and hexagonal plate. So if the glue is not strong enough, you apply.
Yeah. So you have to make sure. So when you do this, if the glue is not strong enough, it may probably do what we started with. There is a defect. That defect is now going to spread across because the stress is higher there. It will just keep on separating. Finally, this sheet will be different, this will be different. Yeah? Any questions? Ask.
This kind of honeycomb structure is what is used in helmets.
Yeah, helmets you can use it, very good. You can use helmets wherever there is no piercing object. For example, is it bulletproof? The answer is no. It will just pierce and that's it. You use it as an armor, you are done. Any more questions? Questions, yeah.
So why would it be using satellites? Because there's like micro meteorites and all hitting it all the time, right? So
no, good question. The assumption made there is if a meteorite hits it, it's gone, over. But it has to be light for the strength. So strength to weight ratio is a very important factor when it comes to aerospace structures, right? So stiffness and strength per unit weight or per unit mass should be high enough for me to make it a candidate material for an aerospace structure. Okay. Time is 11. So I request you to do one thing. And we'll continue tomorrow definitely. We'll take one tray. Put those two materials into this. One is magnetic balls, the other is silly putty. Pass it on so that. Hey folks, have a look at this one. Should I leave it here and go? So that, but don't touch it. Don't touch it so that we can observe what's happening tomorrow. Yeah? Yeah, okay.
Thank you for your wonderful lecture, sir. It was very interesting doing all the experiments. We were understanding many new concepts, and thank you all the teaching assistants. Thank you, sir.
Thank you all. You can't escape from me. Tomorrow also I'm coming.